everyone, welcome to another episode of The Dancing Professor. On today's episode, we're going to be talking about one of my favorite topics, perception. We're going to begin by talking about the difference between bottom-up and top-down processing. We're going to talk about the way that humans actually recognize letters and recognize objects. We're going to talk about perceptual organization with respect to the different Gestalt psychology principles. We're going to talk about the difference between humans versus computers in terms of perception and how this relates to what we call perceptual intelligence versus artificial intelligence. And lastly, we're going to see how perception and attention actually go hand in hand. So perception depends on both incoming stimulation and knowledge that we bring to the situation. So essentially, someone who has no idea what they're looking at is going to perceive a particular object differently from someone who actually does know what they're looking at. And so perceptual intelligence is this particular knowledge that we bring to a situation. So perception depends on both incoming stimulation and knowledge that we bring to a situation. And this is what we call perceptual intelligence. So this means that someone who's going to be looking at something that they've never seen before will perceive that object to be different than someone who actually does know what they're looking at. So perception differs in terms of the amount of information the viewer has when looking or perceiving at it. Bottom-up processing is the idea that when we process or perceive information, this starts with the stimulation of our sensory receptors. We begin with very small details and then we piece them into a bigger picture. Top-down processing starts with a person's knowledge because that person already has previous experience of what it is that he or she is perceiving, and they are based on particular expectations that we use to recognize this particular stimuli. So bottom-up processing refers to when there is no prior knowledge for what is being perceived, and top-down processing is the type of processing used when people do know what they're perceiving. Typically in our daily lives, we're constantly using a combination of top-down and bottom-up processing. And so just to give you a bit of a better understanding, bottom-up processing occurs when we sense basic features of stimuli and then we integrate them into a larger whole. So for example, if you've never seen a bicycle before, right, you'll start with the wheels, then you'll start with the seat, then you might look at the bars, and you'll understand that this is some form of transportation, right? The wheels are intended to move people from one place to another. Top-down processing occurs when previous experience and expectations are first used to recognize stimuli. So if you're looking at that same bicycle and you're very well aware of what it is, you're not going to need to break it down into its smaller parts because you are already aware of what the product or the object is as a whole. And here, this is an example of the flow that a particular person could go through, whether they're using top-down processing or bottom-up. You'll notice that in top-down processing, the particular stimulus and the specific parts of it occur at the bottom, but in bottom-up processing, that's actually where you would start with the different features of the particular stimulus. So in terms of recognizing letters and objects, when we spoke about feature detectors in our memory chapter, we understood that there are specific neurons that respond to different types of senses or different types of stimuli. This leads us to learn about the interactive activation model, which says that activation in our brain is sent through 3 different levels. The first is called the feature level, and this consists of feature units such as lines and curves. The second one is called the letter level, which consists of letter units, and as we know, we have one for each letter in the alphabet. And ultimately, the letters build together to form the word level. And the word level is almost like a person's lexicon, right? All the words a person knows. So recognizing a letter could be presenting the letter K, for example, and activating feature units for K's features. So if we think about it, the feature units for K, we have a straight line, we have a diagonal line coming from up to down, and we have a diagonal line coming from down, from the center towards the bottom. So we have 3 different lines, right? 3 different feature units. This sends activation to letters that contain the same features. So what are some other letters that have a straight line and a diagonal line, or one going this way? So we know that R is another similar letter, right? R has a straight line, then it has sort of a rounded P shape, right? And then from here we have the same feature as the letter K has. So this sends activation to words that contain the same letters. So ultimately, this leads us to recognizing a word. So basically, this theory states that if you understand the units and the features of a particular letter, then you will be able to recognize all the words that contain that letter. So there is a letter unit for each letter's position in a word. So this sends activation to all words with letters in the same position. For example, if you think of the word, I believe I have one here. Nope, I don't. If you think of the word fork, you know that K is the fourth letter in this word. If you can think of that, you can also think of all other words that have K as the last letter in a particular word. So you have fork, pick, black, right? So it becomes much easier for us to find words with the same letter K in the same exact position. We also know that there is such a thing as the word superiority effect, which means that letters are easier to recognize when they are in a word versus when they appear alone or in a non-word. So letters are recognized more quickly and more accurately based on their surrounding context. So this actually directly relates to human factor psychology and to the design of various interfaces. Sometimes designers want to use a particular letter, like Pandora, for example, right, with it, which is just the letter P for the music app. But it's very possible that people may recognize the letter better and more accurately when they see it in the context of a word versus just a standalone letter to act as an icon for a particular product. And so when we talk about non-words, right, so we have the example of fork versus RFOK versus just the letter K on its own. So we're more likely to recognize the letter K in the word fork than when it's in a non-word or than when it stands alone. When it comes to recognizing a letter within a word, this actually creates the feedback activation loop, which says that activation is sent from word units back to letter units for that word. So the word unit is fork. This sends activation to each letter unit, such as K, which is fourth in this word. And so that's the perfect example that we just spoke about. So once you already know the feature units that make up a letter, once you understand the letter that makes up the word and the positioning of the letters in each word, we're much more able to go back and forth between perception of these various different letters and these words. So if we talk about excitation in neural firing, right? So when we spoke about memory, we learned that information travels in neural circuits, right? And when information is passed from one neuron to another, that's via neural firing, or what we call an action potential. Increased or rapid neural firing is known as excitation. And each level excites excitation from one unit to another. Essentially, when excitation occurs, processing occurs much faster. So you're much more able to recognize these letters in these words at a faster rate. Inhibition occurs when you want to stop activation if the units do not correspond. So, for example, let's say the question becomes, name all the words that have K as the last letter. So we said fork, pick, black, and then if you say something like Arkansas, right? K is not the last letter. It does have the letter K in it, but it is not the last letter. So inhibition would occur, and you would not continuously start naming words that has K as the third letter, right? You would actually stop yourself and realize that you've made a mistake. So inhibition is the reduction in speed of neural firing, and excitation is an increase in the speed of neural firing. The faster the neurons are firing, the faster information is traveling. So how does the interactive activation model apply to top-down and bottom-up processing? Well, you can think about learning a new language, right? We're taking all of these examples here for granted because we all speak English, we all can read English, so we can relate to this. However, if you think about when you first started, or if you've ever tried to learn a new language, especially if the letters were in a different alphabet, they were like not Latin letters, for example, Cyrillic or like an Arabic script, you will notice that you would actually start paying much more attention to the feature units before you can even get to the letter units, right? Because the lines may look different. Maybe they're more rounded. Maybe with like Chinese, right, you have the hieroglyphs and they're written down to up instead of left to right. So you start paying much more attention to the actual physical aspects of the features. After you've understood the physical aspects, then you're more able to put those different features into letters, and then after you've learned the letters, then you can actually identify them in words. So in terms of how this relates to top-down and bottom-up processing, top-down processing is when we actually perceive the word immediately, but bottom-up processing is more related to learning a new language, when you actually have to perceive the different feature units that make up the letters that eventually make up the word. Feature integration theory is also another interesting theory where it says that perception is broken up into different stages. The first stage is called the pre-attentive stage, and this happens fairly automatically. So sort of how we were talking about automatic processing, this doesn't require much effort. Also doesn't require much awareness or attention because you're not really conscious of the fact that you're perceiving something. But while you're perceiving it, you're actually analyzing an object into its features. The second stage is called the focused attention stage, where the person actually tries to combine these individual features into one whole to form a larger perception, to form a bigger picture. So is this mostly top-down or bottom-up processing, and why? Well, if it's something that you're aware of, that you know what you're looking at, right, of course that would be top-down processing. But again, if you're looking at something, at a particular object that you're not familiar with, you're probably going to be engaging in bottom-up processing. Directly related to objects and perception of objects and how this applies to human factors is the recognition by components theory. This theory says that features are not lines and curves, right, as the previous model, the interactive activation theory, said, but actually we perceive things in 3D shapes. And the gentleman named Biederman, who coined this term, said that these 3D shapes are called geons. He further goes to explain that most of the things that we perceive in our world can be made up of 36 geons. These are enough to construct the majority of objects in our environment. Additionally, Biederman mentions that these geons have view invariance, which means they can be identified from a variety of different angles, and you could still understand what the object is. For example, I'm going back to my water bottle. If I hold the water bottle this way, you can see it's a bottle. If I hold it this way, you see it's a bottle. If I hold it this way, you could still see it's a bottle. So no matter which angle I hold it at, right, the angle of view becomes invariant, right? It can change, but your view of it does not change. You still understand what it is. You can still identify it. Discriminability is another aspect of these geons, right? Which means that each geon can be distinguished from another. So if we look at the bottle, we have a rounded cap, which could be one geon. We have this cylinder, that's another geon, and we have a bottom circle, which could be a third geon. You could distinguish the different shape of each geon from itself, even though they're combined into one whole object. And lastly, this theory says that these geons are resistant to visual noise, which means that geons can be identified in noisy, not to say loud, but meaning very cluttered conditions, right? So if something is light or dark or cluttered or spacious, you're still able to understand what the object is, even if a shadow is falling on it or if it's in the dark. So ultimately, his argument is that if there's enough information available to identify an object's basic geons, a person will be able to identify and perceive the object correctly. Now we're going to talk about perceptual organization. Perceptual organization sort of gained recognition in the 1920s when Gestalt psychologists introduced the laws of perceptual organization. Gestalt in German means shape or form. And so the Gestalt laws of organization were essentially rules that specified how we perceptually organize different parts into one larger whole. The first law they came up with was the law of simplicity, which says that every structure is seen in its simplest form. So here we see an image of several circles versus other odd shapes. So that means that you would not see a shape like this, right, like a cookie with a part bitten off, or you wouldn't see this, right, just the bottom part of a circle. So the law of simplicity says that we understand that the most simple shape that we could see here is a circle, and this is just 5 different circles overlapped on each other. The second law is the law of similarity, which says that similar things appear to be grouped together. So when you look at something like this, you immediately perceive that these are all squares and these are all circles. And we do that fairly quickly because the things that are similar, they are grouped together. Law of good continuation says that when points are connected, they are seen as a straight or connected line and seen as belonging together or following a smooth path. So for example, if we were to be looking at an image here on the left, you see red dots here at the top and you see gray or black dots here at the bottom, but a person would actually perceive it to be something like this. Perhaps the 2 colors would be different, but essentially we don't view this as a variety of small disconnected points. We would actually view it as something smooth and flowing in one direction because they're continuing in the same place. So the fourth law is called the law of proximity, which says that things that are near each other appear to be grouped together. And you can think about this, you know, in the way that cities are built. You can think about even like where your school is positioned, right? If you think about the food places, right, or food court in a mall, things that serve a common purpose are commonly grouped together. And so, you know, they're proximal, they're close to each other. Law of proximity and law of similarity share a lot of similarities, right? They're pretty close in their definitions, but essentially one says that things that are similar would be grouped together, and the other one says that things that are near each other are grouped together for a reason because they're sort of serving a common cause. Law of common fate says that things that are moving in the same direction appear to be grouped together. So, for example, a flock of birds, right? You wouldn't see all those birds as flying separately when they're all flying perfectly in a one-shaped V. But in a more down-to-earth example, if you look at, you know, traffic on a highway or on a street, you can see that all the people going one direction tend to be moving towards a, you know, common fate. They're moving in the same path. And then the people going in the opposite direction, they're also moving in their own corresponding same path. The last law is the law of familiarity, where things are more likely to be grouped together if they seem familiar or meaningful. So in terms of perception, right, we have a particular part of our brain called the fusiform face area, which is in the temporal lobe, and it's very heavy in neurons that actually help us identify people's faces. So in a sense, when a face is familiar to us, we're more likely to perceive it more quickly and more accurately than if it's someone that we had never seen before or never met. So these Gestalt laws of organization, they provide information for us because they reflect things that we know from experience and constant use. However, they do not always result in accurate perceptions. So in a sense, these Gestalt laws of organization, right, they're not really proven to be true 100% of the time. They're more like guesses or heuristics, predictions, as solutions to a problem. And heuristics may not result in a solution or in a correct solution every time. Of course, the opposite to a heuristic is an algorithm, sort of like a guaranteed solution to a problem. Like a mathematical formula is an example of an algorithm. Every time you do it, no matter who does it, if they're doing it correctly, no matter which calculator you do it on, it's always going to generate the same result. With a heuristic, heuristics are pretty subjective and they can change, you know, from person to person. But algorithms, they lead to the correct answer every time. So why wouldn't we use algorithms over and over if we know that they're more accurate? Well, the reason behind that is that they generally take much longer than using a heuristic to solve a problem. And we know, especially with design or with research, this is a constant you know, point of interest for the two domains, where designers sort of feel like, oh, well, I could fixate on a previous design that I've used before, and you know, it worked last time, so why wouldn't it work this time? By rule of thumb, I could just reuse the same design. And research is more about using algorithms and empirical evidence and, you know, running statistical analyses to actually prove which design is better, which one is worse in terms of the user. Now that brings us to our topic of humans versus computers. So why do computers have such difficulty recognizing objects or recognizing speech? Well, in a computer, objects are seen from just one viewpoint or angle. And this poses the inverse projection problem. Multiple stimuli can produce the same image on a person's retina. So here you can see that when an object is created, when an object is positioned at different angles, the retina can still perceive it to be that same object. Same thing as the view invariance with the water bottle that we discussed. For a computer, things have to be presented at a particular angle for it to actually perceive what it is that you are trying to show it, perceive the stimulus. A great example of this is if you've ever tried depositing checks online through an app, right? You have to hold the phone at a very particular angle so that enough light falls on it, so that everything is maintained within the boundaries of the app's screen. And if it doesn't work, if you don't follow those instructions exactly, then it will not actually work and you're not able to deposit the check. But if a person in the bank holds it one way or the other way or upside down even, they could still understand that it is a check. So it makes it difficult to determine where one object ends and another begins. And a perfect example of this is Photoshop. I don't know if any of you guys actually tried editing photos in Photoshop, but there's this wand tool where you can click and it sort of highlights an entire area that you can erase or edit out. And so what happens if, for example, I'm wearing a red shirt, and if I'm on a red background, it won't understand that my red and the red background behind me are actually two different objects. So that's another example of the inverse projection problem. Separating an overall stimulus into parts is different for a computer, but it's much easier for a human. And also computers may not recognize objects that are blurry or shaded. So another example I have for you here is like a Facebook photo tag. So unless the image is very clear and it is not blurry, the tag will not actually be accurately made. Sometimes it could actually tag the wrong person. Again, it is based on some sort of algorithmic feature representation of faces. However, if it's blurry, then that algorithm becomes not usable. And so, but a person can still recognize who is in the picture even if it's slightly blurry. So it's difficult for computers to recognize speech because they can't understand where one word starts and the other begins. So if you notice, if you or a family member ever had a particular accent from a different language and you tried to use voice commands in a car or in a navigation or even on your mobile phone, sometimes Siri may not understand what it is that you want from her, because unless you enunciate and articulate each word and you speak slowly and you speak clearly and there's no other background noise, the device or the computer will not actually understand what it is that you're trying to say. Additionally, speech segmentation is not easily recognized by computers, and speech segmentation is the organization of speech into individual words. So if you've ever listened to someone speak another language and it just sounds like if you don't understand what they're saying, to you it's going to sound like there's never a pause, right? Especially there are certain languages that speak more quickly than others. However, if you do speak the language, then it becomes very simple for you to understand where one word starts and one begins. Humans can recognize speech or voice commands if there's background noise, right? If a person is not enunciating every syllable, if a person does not pause between the words, right? But a computer can only do this if all of the opposite are true, right? A computer can only do it if the person speaking to it speaks distinctly, if they pause between the words, and if there's no background noise happening. So here I ask, what does this remind you of? For me, again, like I mentioned, I have family members that try to, use Siri or use like a navigation voice command. Sometimes when you're calling a credit card company, like, I did not understand your entry. So sometimes, an accent and intonation even of speech really affects the way a computer can or cannot actually perceive what is being said. So this leads us directly to perceptual intelligence. What do we as humans have that computers don't? Well, we have perceptual intelligence, which says that human perception depends on information from stimuli as well as previous knowledge. This is not to say that computers are not smart, right? They are. They possess a lot of knowledge that's programmable in a way. But there are certain things that they can't work around. And one of those things is called the occlusion heuristic. To occlude something is to block it, to hide it. So basically, when a large object is partially covered by a smaller occluding object, we see the larger one as continuing behind the occluder. So for example, I am standing behind a desk right now, and in front of me is a computer. But you probably know that behind this desk, I have legs, right? Behind this computer, there is more of a body visible. So you understand that I am continuing beyond this desk in quite in a tall way. But a computer may not understand that, right? A computer might see this as one object and the desk as another and not understand that there's anything behind it. And this prevents us from seeing things in the environment as chopped up when they're partially hidden by other objects. So just because something is blocking another thing, we have depth perception. We understand that there are certain things continuing behind things that are blocking. Computers do not have this ability. And so further on perceptual intelligence, why can we identify individual words in conversational speech while computers can't? Well, this goes back to semantics. We have knowledge of the meaning of words. And again, that's why this is only true for languages that you understand. In terms of perceptual organization, let's look at a specific example from a research project. If you read, Jamie's mother said, "Be a big girl and eat your fruits." And then if you hear the sentence, "The thing Big Earl loved most in the world was his dog." In both cases, you have the words big girl and big Earl, which may sound similar, but in context, you understand that Jamie's mother said, "Be a big girl and eat your fruits." In context, you understand that because she's mature, she's trying to encourage her to actually finish her food. And in the second sentence, the thing Big Earl loved most in the world was his dog. Again, the pronoun his refers to Earl, which is a male name. You probably wouldn't hear the thing Big Girl loved most in his dog, in the, sorry, one more time. The thing Big Earl loved most in the world was her dog, because you wouldn't hear big girl given the pronoun his in the sentence. So it really depends on the knowledge of context, even when the words sound the same or similar. Further, we understand that languages have transitional probabilities, which means that there are particular sounds and letters that will follow another sound when we're learning a language. So for example, you know that a lot of adjectives will end in the letters OUS. You will know that whenever there's, for most of the times when there's an IGH, the GH are silent and it's pronounced I, like night, fight, sight, right? In French words, you know that there's often QUO or QUI. There's like a string of particular vowels that follow a consonant. So those are examples of transitional probabilities that we have perceptual intelligence of, and that actually help us in terms of learning. A computer would have to be given a specific code with a variety of exceptions that can identify words, the meaning of words, while we don't necessarily need to be programmed in that way. So statistical learning is another thing, the process of learning about transitional probabilities and other characteristics of a language. So in my experience, I've realized, because I'm very interested in how in intercultural research and international research, and to see how people from different countries who speak different languages interact with various items of technology. And for the most part, at least given in Silicon Valley, we do most of our testing on Americans, right? We do a lot of testing on people who speak English, and then we try to sell our products across the world. But it's really important to get samples of, a representative population from these different countries to see how they in fact would interact with them. And even though they speak the language and they understand how to use it and such, especially with voice control and voice commands, languages have a particular intonation. So they do not always, so even though the participants or the users may be saying the words correctly, the tone of their voice might actually throw the program off, right? So the program is designed to be receptive to a particular tone of voice, to particular speed of voice, to particular pauses. So things like transitional probabilities and statistical learning are really, really important when designing products in human factors, for international consumers. Statistical learning is also important for learning about the world around us, right? Not just for languages. Where do we store, by the way, all of the knowledge that we have about our world? Well, again, this relates back to where we store it in our long-term memory, right? And so over time, our neurons become tuned to respond to specific stimuli. And this is what is known as experience-dependent plasticity. So this phenomenon says that our brains are plastic in a way, which means that they're malleable, right? And the information that we store can be changed, and we can adapt to new information that we learn. So we are able to do that as humans. So if, for example, you are friends with someone who has a very strong accent, right? And instead of water, they'll say water, for example. So this is water bottle, right? Instead of this is a water bottle. Over time, you would probably understand that your friend Olga is trying to say that this is a water bottle. Even though she may be saying it like this, you're still able to understand that she's saying water bottle. So experience-dependent plasticity says that we as people can adapt to various environments. We can adapt to the different ways that people may pronounce things, and we can still get our point across, and we can still communicate. If I spoke that way in a voice command to some device, it probably would not understand me, right? If I was talking to a vending machine, for example, using voice command and I wanted a bottle of water, it's very possible that the machine would not understand me. So being able to adapt, being able to learn, being able to understand different languages, different intonations, different use cases for people around the world is very, very important. But again, it's not possible, it's not available in artificial intelligence, but for humans we do have it in perceptual intelligence. So the solution to this would be to actually program these devices to be sensitive to these various cultural aspects. So what special feature of the brain allows an uncommon stimulus experience to seem more common? Well, again, that relates to experience-dependent plasticity. So the human brain is full of information about the world and how it functions, and we use this information without even being aware that we're doing it. And so this is a big advantage for humans over computers. Humans are intelligent perceivers, and computers are incredibly intelligent as well. And again, as time is advancing, technology is, doing mind-blowing things. Everything from like robotics to things that write your papers for you, right? So computers have this incredible ability to be extremely intelligent. But again, a human has to program it to actually do that. So until we become sensitive to these things and until we understand that all of this variation has to be accounted for in a particular device or in a particular computer, they will never replace a human. They will never replace the intelligence that a human has. Sure, it may calculate things at a much higher rate. It may do things more accurately. It may remove bias and be completely objective in a lot of things. It's very good for like random assignment or sorting things at random. But when it comes to particular obstacles or interferences or occlusions, that's when humans are necessary to intervene. That's when humans can override a particular function in a computer that prevents it from advancing forward. So lastly, we're going to talk about perception and attention. Can we perceive effectively without paying attention? Well, let's try it together. I'm going to show you a quick video, and then we'll see what you guys think.
Hi, I'm Richard, this is Sarah, and we're going to perform the amazing colour-changing card trick with this blue-backed deck of cards. Now the idea is very simple. I'm just going to spread the cards in front of Sarah and ask her to push any card towards the camera.
Right, okay, let's see. I'm going to go for this card here.
Okay. Now Sarah could have selected any card at all from the deck, but she selected the card which is now face down on the table. What I'm going to ask her to do is show us which card she selected.
Right, so the card that I chose was in fact the 3 of diamonds.
The 3 of diamonds, okay, excellent choice. That card goes back into the deck. Now I'm just going to spread the cards face up on the table. Do a little click of the fingers, and you'll see that Sarah's card here has now got a blue back. Not particularly surprising. What's slightly more surprising is all of the other cards have got red backs. And that is the amazing colour-changing card trick. Hi, I'm Richard, this is Sarah, and we're going to perform the amazing colour-changing card trick with this blue-backed deck of cards. Now the idea is very simple. I'm just going to spread the cards in front of Sarah and ask her to push any card towards the camera.
Right, okay, let's see. I'm going to go for this card here.
Okay. Now Sarah could have selected any card at all from the deck, but she selected the card which is now face down on the table. What I'm going to ask her to do is show us which card she selected.
Right, so the card that I chose was in fact the 3 of diamonds.
The 3 of diamonds, okay, excellent choice. That card goes back into the deck. Now I'm just going to spread the cards face up on the table. Do a little click of the fingers, and you'll see that Sarah's card here has now got a blue back. Not particularly surprising. What's slightly more surprising is all of the other cards have got red backs. And that is the amazing colour-changing card trick.
So prior to watching the video, I had asked the question, can we perceive effectively without paying attention? And so I'm really curious to hear what you guys have to say. But in my opinion, if I think about the things that separate sensation from perception, right, both of them depend on the senses. Both of them are relying on incoming information from the environment. But what really sets them apart is, again, this prior knowledge that we have for what we're looking at, right, whether it's top-down or bottom-up processing. But even before that actually happens, sometimes we sense things that we do not pay attention to. And when that happens, that information never makes it into our sensory memory. It never makes it definitely into our short-term memory. And of course, if it's not in short-term or working memory, it will not make it into long-term memory. However, with perception, you actually have to pay attention because perception involves a cognitive process of actually being aware of what it is that you're looking at. So in this sense, perception in my mind is an equation of sensation plus attention. Without attention, you cannot have perception. And so in this particular video, we notice what is called change blindness, right? And this is the fact that we didn't notice, or at least I didn't when I first watched this, the various change in the scenes that were going on. And so the question becomes why? Well, that's because we were so fixated and focused on understanding the color changing card trick that we had devoted all of our cognitive resources to that, and we did not notice all of the other changes. So on that note, I'm going to wrap up our lecture on perception. I hope you enjoyed it just as much as I did. Feel free to subscribe to the channel for more videos. And again, if you have any questions or comments or things that you would like to share on our next program, please feel free to email me at csundancingprofessor@gmail.com. Thanks so much. Thanks for watching.